So this is obviously the Golden Gate Bridge, and I think it's a good depiction of equilibrium, especially the kind we talk about, dynamic equilibrium. This is a time-lapse photo, obviously. These cars going that way, those cars going that way. So there's a constant flow of cars going both ways on and off the bridge. But generally during this time of day, I would assume there's about the same amount of cars on the bridge at any given time. So even though there's a constant flow on and off the bridge, there's still about the same amount of cars on the bridge. And so that's kind of equilibrium. So first off, what is a reaction? Basically, you have molecules moving around. They're all moving around, dancing around, going all over the place. When they smack into each other, you get a reaction. That's the chemical reaction. Those collisions. Types of reactions: homogeneous reactions or heterogeneous reactions. Homogeneous reactions is when they're all the same phase, so they're all a gas, for instance. Whereas hetero would be different. So you got some solids, you got some aqueous, you got some gas going on, different kinds. All right. Well, let's talk about a flask of water. You get yourself a flask of water, you put some water in there, you leave it open, okay? No cork in there. You leave it open, what's going to happen? It's going to evaporate. You're going to have an empty flask. Okay? And you could watch, especially if it was graduated somehow, you could watch that water level drop. All right, now let's say we take another flask, we put, half full of water, and then we cork it. Okay? The water's going to drop eventually. At first, you're going to get a little bit of drop, but then it's going to stop. So you're like, what's going on here? Well, first off, the water evaporated until it filled up the air that was in the container. Then after that, it's still evaporating, but it's also condensing at the same exact speed that it's evaporating. So it's like the bridge, all right? So it has the same amount of water in the flask, but you have water that's constantly becoming water vapor and water vapor that's constantly condensing back and forming water. So they're going back and forth in there. It's just that what you see is a dynamic equilibrium. Okay? They're moving, but the amount leaving is equal to the amount coming. So they balance each other out. All right. Equilibrium constant. Consider the following equation. So this is basically saying you have A number of A's, B number of B's, C number of C's, and D number of D's. Right, the capital letters are the species. So carbon dioxide, oxygen, water, sugar, whatever. And then those would be the coefficients in front of them. And of course, as I'm sure you're aware with chemical equations, you don't always have 2 on the left and 2 on the right. You can have any number on any side. All right. So this is the equation for the equilibrium constant. Basically, what this is saying is that at any given temperature and pressure, there's going to be an equilibrium constant for any given reaction. Now, I don't know if that makes a lot of sense, but let me see if I can't help you out with that a little bit. Here's the equation, first off. So you take the concentration, brackets means concentration, right? The concentration of C to the power of its coefficient times concentration of D to its coefficient, right? So it's basically the concentrations of all of their products to the power of their coefficients multiplied together divided by the exact same thing of the reactants. And for any given reaction, that is always going to equal the same number. So, for instance, here we go. Oh, by the way, you only do gases. Any liquids or solids become a 1. You just plug a 1 into their place or whatever. So, it's good to know, I think. Anyways, what's the equilibrium expression for this, right? So, it's the concentration of HF squared divided by the concentration of H2 times the concentration of F2. If I gave you numbers for all three of those things, you could plug them in and solve for K. But K is always constant. So the equilibrium constant for this reaction is some number I don't know off the top of my head. Okay, but that's always the same number. So if you were to add H2, it would move in a way, right, it would create as much HF as was necessary to make this math come out to be the exact same constant every time. And you'll see some more examples of that. All right, so give this one a shot. If you have the equation 2S2 plus O2 gives you 2SO3. And those are your concentrations S2 or SO2, O2, and SO3. Solve for K. Not bad. Let's go back and do it. So, you're going to go concentration of SO3 squared, so you're going to have 3.50 squared divided by 1.50 squared times 1.25.
That was how I did it.
That's how you did it?
Well, my first answer was wrong, but my second answer, I just did.
Okay. So if you do that out, what do you get for an answer? 4.36? Sounds about right. That's a good pepper. So that was for homogeneous. Okay, this is for heterogeneous equilibrium. So what you do, chemical equilibrium, or the equilibrium constant I should say, is not impacted by liquids or solids. So they all become a 1. So in this case, it's the concentration of this times the concentration of this divided by concentration of this. Well, this just turns into a 1 because it's a solid. So it's 1 times this divided by 1, so it's just the concentration of your CO2. So the only thing you work with is gases. You ignore the liquids. You don't really ignore them. You make them 1. So give this beast a try. Because this becomes a 1, this becomes a 1, so it's just 0.50 times 1 divided by 1, 0.50.
Well, Marcus, why don't you put 0?